Hey, sleepers. Tonight, we're journeying to the edge of understanding, to a place where the rules of the cosmos seem to bend and break. We are traveling on whispers of light, across unfathomable distances, to meet a ghost in the machine of the universe. Imagine a velvet blackness, deeper than any night you have ever known. In this endless expanse, tiny diamonds of light are scattered. Some are sharp and brilliant. Others are soft, hazy glows. We are floating here, weightless and calm, looking toward the constellation of the twins, Gemini. And in that patch of sky, something is hiding. Something that, for a moment, made us question everything we thought we knew about the life and death of stars. It's a story of discovery, of mystery, and the beautiful, humble process of science itself. It is a story about the black hole that shouldn't exist. So before you get comfortable, take a moment to like the video and subscribe. It helps our small corner of the cosmos reach other sleepy stargazers like you. And while you're there, feel free to share your location and your local time in the comments below. It's always wonderful to imagine us all scattered across the globe, looking up at the same immense sky, all at different moments in our day, but connected by curiosity. So close your eyes, take a deep breath, and get ready to drift off as we explore the gentle mystery of a cosmic anomaly. Our story begins not with a bang, but with a quiet observation. It begins in the year 2019 with a team of astronomers in China, led by a scientist named Jifeng Liu. They were using a remarkable instrument, a telescope with a name that sounds like a gentle hum. LAMOST, the Large Sky Area Multi-Object Fiber Spectroscopic Telescope. That's a mouthful, so let's just think of it as a giant, patient eye. Unlike telescopes that stare intently at one tiny spot, this one is designed to look at a huge patch of sky all at once. It has thousands of tiny robotic arms, each holding a fiber optic cable, like a robotic octopus with eyes on the end of each tentacle. These arms can be precisely positioned to capture the light from thousands of individual stars simultaneously. It is an incredibly efficient way to survey our galactic neighborhood, to create a grand map of the stars and their movements. For years, this telescope had been patiently gathering light, night after night, building a library of starlight. In this vast library, every star has its own story, written in the language of light. And the team in China were the librarians, carefully reading these stories. One of the things they looked for were stars that weren't standing still, or rather, stars that seemed to be dancing with an invisible partner. Imagine you are looking at a single dancer on a dark stage. If they are moving in a straight line, that's one thing. But what if they are moving in a circle? You would immediately know they have a partner, even if you couldn't see them. You could learn a lot about that unseen partner just by watching the visible dancer. If the visible dancer is making a wide, slow circle, their partner is likely far away. If they are whipping around in a tight, fast circle, their partner must be very close and very heavy, pulling on them with a strong gravitational grip. This is precisely what astronomers do. They look for a star that is wobbling. Not a physical wobble, but a wobble in its light. As a star moves toward us in its orbit, its light gets squished a little bit. The waves of light get compressed, shifting toward the blue end of the spectrum. This is called a blue shift. As it moves away from us, its light gets stretched out, shifting toward the red end of the spectrum. This is called a redshift. It's the exact same principle as the sound of an ambulance siren. The pitch sounds higher as it comes toward you, and lower as it drives away. Astronomers can measure this tiny shift in the starlight with incredible precision. By watching a star's light shift back and forth, from blue to red and back to blue again, they can trace its orbit. And from the speed and shape of that orbit, they can calculate the mass of its invisible companion. The team was sifting through data, looking for these stellar dances, and they found one. A particular star, located about 13,800 light years away from us, in the direction of the constellation Gemini. Now, a light year is a measure of distance, not time. It's the distance light travels in 1 year. Light is the fastest thing in the universe, so a light year is a truly enormous distance. 13,800 of them is almost incomprehensibly far. To put it in perspective, the light from this star that the telescope captured began its journey to Earth long before the first human civilizations began to build cities or write down their histories. It is a postcard from the distant past. This star was a B-type star. In the cosmic classification system, stars are a bit like students in a school. There are the small, cool, long-lived red dwarfs, the steady, middle-of-the-road yellow stars like our sun, and then there are the big, brilliant, hot-headed B-type stars. They are giants. Bright, blue, and beautiful. They live fast and die young. This particular B-type star was about 8 times more massive than our sun. A hefty star, to be sure. And it was dancing. The astronomers watched its light. They saw it shifting from blue to red and back again over a period of about 79 days. A slow, graceful cosmic waltz. This told them the star was in a very wide orbit with its unseen partner. From the speed of its wobble, they did the math. They calculated how much gravitational pull was needed to swing an 8 solar mass star around in such a wide orbit. The number they came up with was shocking. The invisible partner, the object pulling on this giant star, had to be 70 times the mass of our sun. 70. Let's pause and let that number sink in. 70 suns. All of that mass compressed into a single point of infinite density from which not even light can escape. An object so massive, yet completely invisible. It could only be one thing, a black hole. But not just any black hole. This was a monster, a giant. And according to everything we thought we knew about how stars live and die in our corner of the universe, it was a black hole that simply should not exist. The discovery was announced in November of 2019, and the astronomical community was stunned. They had found an impossible creature lurking in our own cosmic backyard. They named the system LB1, and with that, a beautiful scientific mystery began to unfold. To understand why a 70 solar mass black hole was so shocking, we need to take a gentle step back and talk about the lives of stars. Think of the universe as a grand cosmic kitchen. The main ingredients are vast clouds of hydrogen and helium gas, left over from the Big Bang. We call these clouds nebulas. Imagine a beautiful, swirling cloud of colorful dust and gas, stretching for light years. It's mostly empty space, but gravity is patient. Over millions of years, gravity gently nudges the gas and dust particles closer together. Clumps begin to form. As a clump grows, its gravity gets stronger, pulling in more material. It gets denser and denser, hotter and hotter in its core. It's like kneading a ball of dough. The more you work it, the warmer it gets. Eventually, the core of this collapsing cloud becomes so hot and so dense that something incredible happens. Nuclear fusion ignites. Hydrogen atoms, the simplest element, are slammed together with such force that they fuse to become helium atoms. This process releases a tremendous amount of energy. It is the same process that powers our sun. This outward push of energy from fusion perfectly balances the inward pull of gravity. A star is born. It is a magnificent, self-sustaining balancing act between gravity trying to crush it and fusion trying to blow it apart. And for millions or even billions of years, it will hang in this stable state, shining brightly. Now, the life of a star is determined almost entirely by one thing: its mass, how much stuff it started with. Low-mass stars, like red dwarfs, are very frugal with their fuel. They sip their hydrogen slowly, and they can live for trillions of years, far longer than the current age of the universe. They will eventually fade away gently into a small, dense cinder called a white dwarf. Medium-mass stars, like our sun, live for about 10 billion years. When they run out of hydrogen in their core, they swell up into a red giant, and then they puff away their outer layers, leaving behind a beautiful glowing shell of gas called a planetary nebula. At the center, a white dwarf remains. But massive stars, the ones more than about 8 times the mass of our sun, live very different lives. They are the rock stars of the cosmos. They burn through their fuel at a furious rate. They are bigger, hotter, and vastly more luminous. Because they are so massive, their cores get much hotter and denser than the core of a sun-like star. So, when they run out of hydrogen, they don't just stop. They begin fusing helium into carbon, then carbon into neon, neon into oxygen, and so on, creating heavier and heavier elements, like a cosmic blacksmith forging new materials in its fiery heart. The core of a massive star, just before it dies, looks like an onion, with layers of different elements. Iron is the final product. Fusing iron doesn't release energy, it consumes it. So when the core of a massive star becomes iron, the fusion engine suddenly shuts off. The outward push of energy that was holding the star up for millions of years vanishes in an instant. Gravity wins, catastrophically. The core collapses in on itself in less than a second. The outer layers of the star come crashing down onto this incredibly dense, newly formed core. They bounce off, creating a shockwave of unimaginable power. The star explodes in a supernova. For a brief time, a single exploding star can outshine its entire galaxy, a blaze of glory visible across the universe. What's left behind depends on the mass of the core. If the core is not too massive, the collapse is halted by a quantum mechanical principle. The particles of the core are squeezed so tightly together that they can't be squeezed any further. A neutron star is born, a city-sized ball of matter so dense that a single teaspoon of it would weigh more than all the cars, trucks, and ships on Earth combined. But if the star was truly massive, if its core is more than about 3 times the mass of our sun, then nothing can stop the collapse. Not even the strange rules of quantum mechanics. Gravity is all-powerful. It crushes the core down to an infinitely small point, a singularity. A black hole is born. A region of space-time where gravity is so strong that nothing, not even light, can escape. So we know how stellar black holes are made. They are the corpses of giant stars. But there's a catch, and it's a very important one. Massive stars are not very good at holding on to themselves. Throughout their lives, they have incredibly powerful stellar winds. They are constantly blowing away their outer layers into space. It's like a pot of water boiling so violently that it's constantly losing steam. The more massive the star, the stronger its stellar wind. This is where another crucial ingredient comes in: metallicity. In astronomy, metals is a slightly funny term. It means any element that isn't hydrogen or helium. Carbon, oxygen, iron, all the things that make up you and me and the planet we live on, are considered metals. These metals are created inside stars and then scattered through the universe by supernova explosions. So each new generation of stars is born from clouds of gas that have been enriched with the metals from previous generations. Stars in our Milky Way galaxy, especially in our neighborhood, are relatively metal-rich. Why does this matter? Well, these metals in a star's atmosphere are very good at catching the light pushing up from the core. They act like tiny sails, and this helps to drive the stellar wind. A metal-rich star has a much stronger stellar wind than a metal-poor star. It loses mass much more efficiently. It's like the difference between trying to blow a smooth billiard ball across a table versus trying to blow a fluffy feather. The feather catches the wind much better. So a very massive star, born in a metal-rich environment like the Milky Way, will blow away a huge fraction of its mass over its lifetime. It might start out with 100 times the mass of the Sun, but by the time it's ready to go supernova, it might have shed more than half of that mass. This puts a natural cap on how massive a black hole can be when it's formed from a single star's collapse. Based on our best models of stellar evolution, for a star in our galaxy, that cap is around 25, maybe 30 times the mass of the Sun. So, a 30 solar mass black hole is a big one, but it's plausible. A 70 solar mass black hole? That's not just a little bit bigger. It's in a whole different league. It breaks the model. But the problem gets even deeper. There is another, even more dramatic way for a star to die, and it creates a forbidden zone for black holes. This process is called a pair instability supernova. It happens to stars that are in a very specific mass range, roughly between 130 and 250 times the mass of our Sun. In the core of these colossal stars, the temperature gets so incredibly high that the light itself, the gamma-ray photons, are energetic enough to spontaneously transform into pairs of particles: an electron and its antimatter counterpart, a positron. This is a real phenomenon, predicted by Einstein's famous equation, E equals mc. Energy can become matter. This creation of particle pairs has a dramatic effect. It removes energy from the core. The photons that were helping to hold the star up against gravity are suddenly gone, converted into matter. The pressure drops. The core begins to collapse. This collapse triggers a runaway thermonuclear explosion. It's so violent, so utterly complete, that it blows the entire star to smithereens. Nothing is left behind. No neutron star. No black hole. Just an expanding cloud of gas and dust. The star literally obliterates itself. Think of it like a cosmic sneeze. A normal supernova is a powerful sneeze where you still have a body left afterward. A pair instability supernova is a sneeze so powerful it vaporizes the person sneezing, leaving not a trace behind. This creates what astronomers call the upper mass gap. Stars that are massive enough to become black holes, but not quite massive enough to trigger this pair instability process, will collapse and form black holes up to about 50 or 60 solar masses. Stars that are in the pair instability zone, from about 60 to 130 solar masses, get completely destroyed, leaving no black hole at all. And stars even more massive than that, above 130 solar masses, are so huge that even this runaway explosion isn't enough to unbind them. They collapse directly into very massive black holes. So, there should be this desert, this gap in the data between about 60 and 130 solar masses, where we find no stellar black holes. It's a forbidden zone, a place where the universe doesn't make black holes from single stars. And yet, there was LB1, a black hole sitting comfortably at 70 solar masses, right in the middle of this forbidden desert. It was like finding a polar bear sunbathing in the Sahara. It didn't make any sense. It defied the beautiful, carefully constructed theories of how stars live and die. This was the heart of the mystery. The black hole that shouldn't exist was a direct challenge to our understanding of the cosmos. Science is a wonderful process. It is not a collection of unchanging facts, but a living, breathing conversation. A discovery is made, a theory is proposed, and then other scientists from all around the world look at the discovery. They test it, they poke it, they try to see it from a different angle. This isn't about proving someone wrong. It's about everyone working together to get closer to the truth. It's a collaborative search for understanding. And this is exactly what happened with the story of LB1. The announcement of a 70 solar mass black hole sent ripples through the scientific community. It was an exciting, but also deeply puzzling result. So other teams of astronomers immediately turned their own telescopes toward this system. They wanted to see it for themselves, to re-examine the evidence. The original measurement was based entirely on the wobble of that bright blue companion star. The whole calculation of the black hole's mass depended on getting the star's motion exactly right. Let's return to our analogy of the dancer on a dark stage. Imagine you are trying to figure out the weight of the invisible partner just by watching the visible dancer. The speed of the dancer is important, yes, but there's another crucial piece of information you need: your viewing angle. Are you watching the dance from directly above, looking down on the circular path? Or are you watching from the side, at the same level as the stage? If you're watching from the side, you won't see a circle at all. You'll just see the dancer moving back and forth, toward you and away from you. They will seem to be moving fastest when they are at the front and back of their circular path, and they will seem to momentarily stop when they are at the sides. If you assumed they were just moving back and forth in a straight line, you might get a very different impression of their speed, and thus a very different calculation for the mass of their partner. This viewing angle in astronomy is called the orbital inclination. An inclination of 90 degrees means we are seeing the orbit edge on. An inclination of 0 degrees means we are seeing it face on. The problem is, for a system like LB1, it's very difficult to measure the inclination directly. The original team had to make an assumption. They assumed a reasonable, average inclination for their calculations. But what if that assumption was wrong? Several other research groups, one led by a scientist named J. Eldridge, and another by Michael Abdul-Masih, took a closer look. They didn't just reanalyze the same data. They used different techniques. They looked very carefully at the light from the B-type star itself. Stars are not perfect, uniform balls of light. They have features in their light spectrum, dark lines called absorption lines. These lines are like a star's fingerprint. They tell you what elements the star is made of, its temperature, and its rotation. One team noticed something peculiar about one of the most prominent lines in the star spectrum, a line from hydrogen gas called the A-alpha line. This line wasn't just wobbling back and forth with the rest of the star's light. It seemed to have its own separate motion. It was almost stationary. This was a huge clue. Here's a possible explanation. The B-type star is so big and bright that it has a strong stellar wind, as we discussed. It's constantly blowing gas off its surface. Some of this gas is pulled toward the black hole, forming a swirling disk of material around it, called an accretion disk. This disk of gas would be glowing, and it would be producing its own light, including that ace-alpha light. Because the disk surrounds the entire system, some parts of it are always moving toward us, and some parts are always moving away from us. When you average it all out, the light from the disk itself would appear to be mostly stationary. The original team had interpreted all the light they saw as coming from the wobbling star. But if some of that light was actually coming from a stationary disk of gas around the black hole, it would contaminate the measurement. It would be like trying to measure the speed of a single car in a traffic jam by looking at the blurry light of all the cars at once. The stationary light from the disk could be tricking the astronomers, making the star's wobble seem much larger than it actually was. It was as if our dancer on the dark stage had a glowing stationary scarf swirling around them. The light from the scarf would mix with the light from the dancer, making it very hard to tell the dancer's true speed. If you corrected for this extra light, if you could digitally subtract the light from the glowing gas disk, you were left with a much smaller wobble for the star itself. When these new teams redid the calculations with this smaller, corrected wobble, the numbers changed dramatically. The invisible partner was no longer a 70 solar mass monster. It was much, much smaller. The new estimates placed its mass somewhere between 5 and 10 times the mass of our Sun. A perfectly normal, well-behaved stellar mass black hole, the kind we expect to find all over our galaxy. The impossible creature, it seemed, had vanished. Another scientist, Ireneusz Szyszynski, proposed yet another elegant solution. Perhaps the system wasn't a black hole and a normal B-type star at all. He suggested it could be a normal star orbiting a stripped-down, super-dense helium star, the kind of remnant left behind after a star has had its outer hydrogen layers siphoned off by a companion. This would also explain the observations without needing a black hole at all. This back and forth is the soul of science. It's a detective story played out across light years. The initial discovery was a bold and fascinating claim based on the best available evidence. But science requires extraordinary evidence for extraordinary claims. The follow-up studies provided a more conventional, less exotic explanation that fit the data more neatly. It showed that the universe is subtle. The story of LB1 shifted from being about an impossible object to being a perfect example of the scientific method at work. A mystery, a hypothesis, a challenge, and a refined understanding. The monster was tamed. The polar bear in the Sahara turned out to be a mirage, caused by the shimmering heat haze. But here is where our story takes another fascinating turn. Even as the case for LB1 being an impossible black hole was weakening, something else was happening in a completely different branch of astronomy. The mystery of the mass gap, the forbidden zone for black holes, was far from solved. In fact, it was about to get much, much deeper. LB1 might have been a false alarm, but the universe, it turns out, really is making monsters. We just needed a new way to see them. So let's say that LB1 is, in fact, a normal black hole. The mystery of that particular star system might be solved. But the question it raised still hangs in the air like a beautiful resonant chord. If not there, then where? How could the universe possibly create a black hole in that forbidden mass gap between roughly 60 and 130 solar masses? The models of single-star evolution seem very clear on this point. A single, isolated star, born in the Milky Way, just can't do it. But what if the star isn't isolated? What if there are other ways to build a black hole? Ways that go beyond the simple life story of one star. Astronomers are incredibly creative thinkers. They are constantly imagining new cosmic recipes. Let's explore some of the beautiful and exotic possibilities they have come up with. One of the most compelling ideas is called hierarchical merger. Or, to put it more simply, black holes building themselves up by eating other black holes. Imagine a place in the universe that is incredibly crowded. Not a city, but a star cluster. A globular cluster, to be specific. Picture a glittering spherical swarm of hundreds of thousands, or even millions of ancient stars, all packed together in a relatively small volume of space. They are like a beehive of suns. In such a dense environment, things can get very dynamic. Stars orbit each other, they have close encounters, they can be thrown out of the cluster, or they can collide. In the chaotic heart of a globular cluster, it's a gravitational dance party. Now, in a cluster this old, all the massive stars would have lived their fast lives and died long ago, leaving behind a population of black holes. So the core of the cluster would be filled with these stellar mass black holes, maybe 10, 20, or 30 times the mass of the Sun. And they too are moving around, caught in the cluster's deep gravitational well. Every now and then, two of these black holes will find each other. They'll be captured into a binary orbit, circling each other faster and faster. As they dance, they radiate energy away in the form of gravitational waves, ripples in the fabric of space-time itself. This loss of energy causes their orbit to shrink. They spiral closer and closer, until finally they merge. In a final, violent collision, they become a single, larger black hole. So if you start with two 20 solar mass black holes, they might merge to form a new black hole with a mass of about 39 solar masses. You might wonder, where did that one solar mass go? It was converted directly into energy, into that powerful burst of gravitational waves. Now you have a 39 solar mass black hole, a new king in the cluster. It's more massive, so it tends to sink toward the center of the cluster. And there, it might encounter another black hole, and the process can repeat. A merger of this 39 solar mass black hole with, say, another 20 solar mass black hole could create a new one with a mass approaching 60 solar masses. You can see how this works. It's a cosmic assembly line. You can build a massive black hole, piece by piece, through a series of mergers. This process could, in principle, create black holes that land squarely in the middle of the forbidden mass gap. It's an elegant way to bypass the rules of single-star evolution entirely. You don't grow a giant tree from a single seed. You bundle many smaller branches together. Another beautiful idea takes us back to the early universe. As we discussed, the metallicity of a star, the amount of cosmic spice in its mixture, has a huge effect on how much mass it loses through stellar winds. Stars in the Milky Way today are metal-rich. But what about the very first stars in the universe? They were born from the pristine clouds of hydrogen and helium, created in the Big Bang. There were no previous generations of stars to enrich these clouds. These first stars were metal poor. Essentially, they contained no metals at all. Without those sails of heavy elements in their atmospheres to catch the light, These ancient stars would have had very weak stellar winds. They would have been very bad at losing mass. So a star that started its life with 150 solar masses could have held onto almost all of that mass throughout its entire life. When it finally reached the end and collapsed, it could form a truly enormous black hole, perhaps 130 or 140 solar masses, leaping right over the mass gap. While these ancient first-generation stars are long gone, it's possible that some stars in very old, metal-poor environments, like small dwarf galaxies that orbit our own Milky Way, could still follow a similar path. They are living fossils from a younger, purer cosmos. So, finding a 70 solar mass black hole could be a clue that it was born not in our modern, enriched galaxy, but in a much more ancient and primitive environment, and is perhaps a visitor from another place. There's a third possibility, a slight twist on the story of a single star's death. It involves finding a loophole in the rules of the pair instability supernova. Remember, that's the process where the star blows itself to smithereens, leaving nothing behind. The models that predict this are complex, and they might not be telling the whole story. What if the star is rotating extremely rapidly? The centrifugal force from the rotation could help to support the star's outer layers, preventing the explosion from being completely successful. Or perhaps the explosion happens, but the star is so massive that not all of the material can escape its immense gravity. A significant portion of it falls back onto the collapsed core. This is called fallback. So the star tries to obliterate itself, but it fails. It sneezes, but then inhales most of the sneeze right back in. This could allow a star that was technically in the mass gap to leave behind a massive black hole after all. The rules are not so much broken as they are cleverly bent. Finally, there is the most exotic idea of all, primordial black holes. These are not the ghosts of dead stars. These are thought to be relics from the very first second of the universe's existence. In the incredibly dense, hot, turbulent soup of the early universe, it's possible that some regions were so dense that they collapsed directly into black holes without ever having been a star. These primordial black holes could come in all sizes, from the mass of an asteroid to thousands of times the mass of the sun. While this is a fascinating idea, most scientists believe it's unlikely to be the explanation for objects like the one thought to be an LB1, as we have more plausible astrophysical explanations. But it remains a tantalizing possibility, a whisper from the dawn of time itself. Each of these theories, hierarchical mergers in crowded clusters, the collapse of ancient, metal-poor stars, or exotic supernova physics, paints a different picture of the universe. They remind us that the cosmos is a complex and wonderful place, with more than one way to achieve a result. The initial puzzle of LB1, even if it turned out to be a misunderstanding, served a vital purpose. It forced astronomers to think creatively, to push the boundaries of their models, and to ask, if a black hole this massive did exist, how could it possibly have been made? The answer was not a dead end. It was the opening of several new and exciting pathways of discovery. And it turned out we were going to need them, because proof that the mass gap was not empty at all was about to arrive, not as a faint glimmer of starlight, but as a vibration in the fabric of space-time itself. For nearly all of human history, our only way of studying the universe was through light. We built bigger and better eyes telescopes to see fainter and more distant objects. We learned to see in different kinds of light, from radio waves to gamma rays. But we were always, in a sense, just watching. We were spectators. But in the 21st century, humanity developed a new sense. We learned how to listen to the universe. We learned to hear the sound of space-time itself. This new sense comes from an incredible set of observatories called LIGO and Virgo. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. There are 2 of these observatories in the United States, one in Washington State and one in Louisiana, and a third, Virgo, is in Italy. They are some of the most sensitive instruments ever built by human beings. Let's try to visualize one. Imagine 2 long tunnels, each 4 kilometers long, arranged in the shape of an L. Inside these tunnels, a powerful laser beam is split in 2. One half travels down one arm, and the other half travels down the other. At the end of each arm is a perfectly polished mirror. The laser beams bounce off these mirrors and travel back to the corner where they started. There, they are recombined. If the 2 arms are exactly the same length, then when the 2 light waves come back together, they should line up perfectly and cancel each other out. A detector is placed at that meeting point, and in a perfect world, it would see nothing but darkness. But we don't live in a perfect world. We live in a dynamic universe. According to Albert Einstein's theory of general relativity, massive objects warp the fabric of space-time around them. Think of space-time as a giant, stretched-out rubber sheet. A planet or a star is like a bowling ball placed on the sheet, creating a dip. And when massive objects move, they create ripples in this sheet, like a boat moving through water. These ripples are gravitational waves. They travel across the universe at the speed of light. They are incredibly faint. By the time they reach Earth, they are stretching and squeezing space-time by an amount that is almost unimaginably small. A gravitational wave passing through a LIGO detector will stretch one arm by a tiny fraction while squeezing the other. We are talking about a change in length that is 10,000 times smaller than the width of a single proton. It is an absurdly small measurement, and yet LIGO can detect it. That tiny change in arm length means the 2 laser beams no longer travel the exact same distance. When they recombine, they are no longer perfectly out of sync. A little bit of light leaks through to the detector, and with that flicker of light, we have heard a whisper from the distant cosmos. What kind of events are powerful enough to create these cosmic tremors? The most powerful events we know of are the collisions of black holes and neutron stars. In 2015, for the first time in history, LIGO detected the signal of 2 black holes spiraling into each other and merging. It was a sound, a chirp, that swept up in frequency, the sound of the universe's most extreme event. It was a discovery that won the Nobel Prize and opened a brand new window onto the universe. We had entered the era of gravitational wave astronomy. For years, LIGO and Virgo listened. They detected dozens of these mergers. They were mapping out the population of black holes in the universe, not by seeing their light, but by hearing their final, violent moments. They were weighing the black holes that participated in these cosmic collisions, and they started to find some very interesting things. They found plenty of black holes in the normal range 10, 20, 30 solar masses. But they also started to find some that were pushing the boundaries. 40 solar masses, 50. They were creeping up to the edge of the forbidden mass gap. And then, in May of 2019, just a few months before the announcement of LB1, LIGO and Virgo detected something truly extraordinary. The signal was short, just a handful of wiggles. It was from an event that happened billions of light years away. They called it GW190521. The GW stands for gravitational wave. The numbers are the date it was detected. 2019, the 5th month, the 21st day. When scientists analyzed this faint tremor, they pieced together the story of what had created it. It was the merger of two black holes. But these were not your everyday stellar mass black holes. One of them was about 66 times the mass of the Sun. The other was about 85 times the mass of the Sun. Both of them were sitting squarely in the middle of the pair instability mass gap. They were two impossible black holes. They were the very things that our theories of single-star evolution said could not be made. And when these two impossible objects merged, they created a new, even larger black hole. The final product was a behemoth of about 142 solar masses. This was the first definitive detection of what is called an intermediate mass black hole, a long sought-after link between the smaller stellar mass black holes and the supermassive black holes that live at the centers of galaxies. The discovery of GW190521 was a watershed moment. It was undeniable proof that the mass gap is not empty. The universe is absolutely making black holes in this forbidden range. The controversy around LB1 almost didn't matter anymore. Even if that specific candidate was a false alarm, the phenomenon it pointed to was real. The mystery was real. The polar bear in the Sahara was real. We just had to look for it with gravitational ears instead of light-based eyes. This one gravitational wave event beautifully vindicated all the creative theorizing that astronomers had been doing. How do you make an 85 solar mass black hole? You probably can't get it from a single star, but you could absolutely get it through a hierarchical merger. Perhaps that 85 solar mass black hole was itself the product of a previous merger of a 40 and a 45 solar mass black hole. The event GW190521 was likely the sound of a second generation or even third generation black hole merger happening in the chaotic heart of a dense star cluster billions of years ago. It's a beautiful convergence of evidence. The puzzle of LB1, which started with light, pushed theorists to think of new ways to build massive black holes. And gravitational waves, a completely different way of sensing the universe, came along and provided the definitive evidence that these creative theories were needed. The universe is more clever, more varied, and more surprising than our simple models might suggest. This is not a failure of our theories. It is a triumph. It shows us where the edges of our knowledge are. It points a giant cosmic arrow toward the areas we need to study more. It tells us that our models of stellar winds, of supernova explosions, of life in dense star clusters are incomplete. There are new physics, new processes, waiting to be understood. The story of the black hole that shouldn't exist is not really a story about a single object anymore. LB1 was the messenger, the catalyst for a deeper conversation. It was a gentle question whispered to us across thousands of light years. And the answer came rumbling back as a vibration in space-time from halfway across the universe. The answer was, you have more to learn. And isn't that a wonderful, peaceful thought? That as much as we know, as much as we have discovered, this vast, beautiful, silent universe still holds secrets. It still has surprises for us. There are still mysteries hiding in the dark, waiting for a patient eye or a sensitive ear to find them. The story of science is a story of humility. It's about being willing to be surprised, to be proven wrong, and to adjust our understanding in the face of new evidence. As you drift now into a comfortable and peaceful sleep, think of that grand cosmic dance, the quiet, patient work of astronomers sifting through libraries of starlight, the creative spark of theorists imagining new cosmic recipes, the incredible ingenuity of engineers who build machines that can feel the vibrations of space-time itself, all of them working together across continents and across disciplines to piece together the story of our universe. The black hole that shouldn't exist turned out to be a key. It didn't open the door we expected. Instead, it pointed us to a completely different door, one we were just learning how to listen at. And through that door, we are beginning to hear the symphony of the cosmos in a way we never could before. A symphony of colliding worlds, of merging giants, and of the deep, silent hum of space-time, carrying the stories of a universe that is far more wondrous and mysterious than we can ever fully imagine. So rest now. Let these great cosmic mysteries cradle you. There is peace in the not knowing. There is comfort in the vastness. And there is beauty in the endless, gentle, and collaborative quest for understanding. Sleep well.